Right, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 360 control system. And today is our 24th lecture. Can you guys hear me? And also being able to see my shared screen here. All right, thank you, Noah. All right, let's move on. Okay, today is a new model. Not new model, it's new module. Okay, new module 8. Frequency response. Okay, and I will try to finish, well, at least the most part of it, if not all of them, by today's lecture. So please follow and keep high concentration here. Okay, frequency response probably is not the new concept to many of you. But let's study it in systematic manner so that you can understand in depth about the frequency response. Okay, so the first concept is, what is the frequency response? What is it? Frequency response, because the first reaction in your mind probably is time response, right? We learned time response in previous module. So what does it mean by frequency response then? It's very easy, right? If you recall the time response, it means what? Your x-axis is time t, right? In unit of second, generally speaking, right? Okay. So x-axis is time t. This is time response. The frequency response following the same idea. The x-axis is what? It's frequency, or omega maybe. F is in hertz. Omega is obviously in radian per second. Okay. So the frequency. Okay. X-axis is frequency. Okay, this is frequency response. And in this course, we are just to talk about the Bode plots. Okay, Bode plots is the frequency response we are studying in this course. Okay, because there is another one that's called Nyquist diagram. We don't study that in this course. Okay, and we only focusing on the Bode plots. Right. So Bode plots, I believe many of you know. We have two, right? Bode plots include two plots, basically. And not a surprise that both plots are with respect to the frequency f, okay, or omega. That's fine. So who knows which and which in Bode plot? This is the Bode plot. Okay, and just as simple as this. Right? And how we generate the Bode plot? MATLAB or AC analysis in Multisim, right? Because we, I think you guys learned the Bode plot by first time in electronic circuit class, okay? In where we use the Multisim to do the AC frequency sweeping analysis. Okay, you generate the gain and phase Bode plots. Okay, and what matter is actually, first of all, given a transfer function like this, okay, given the transfer function like this, given the transfer function like this, okay, it's actually either closed loop, of course here, we just either open loop transfer function or closed loop transfer function. We can correspondingly generate the open loop Bode plots and closed loop Bode plots, respectively. Okay. So first thing you need to understand, we could have either open loop body or closed loop body. Okay. Based on different transfer function. Okay. Open loop body means what? Means you are using open loop transfer function. Closed loop body means what? It means you're using closed loop transfer function. Okay. That's very easy to follow, right? We could have either or. Okay. We have both actually. Okay. Both are meaningful. Of course, for different things. Okay. Maybe you see what's the difference. Okay. This is the first thing you need to keep in mind. You might use open loop transfer function or closed loop transfer function. Okay. The second thing you need to understand how we come up with gain and the phase as a function of frequency. Okay. How we come up with the gain and the phase of the transfer function as the function of frequency. Does it make sense? So G of S, of course, it has magnitude. And the phase. Right? And the magnitude is function of frequency. So is the phase. Okay. So you need to understand how we come up with these two function of frequency, right? So first of all, let's talk about the magnitude. How we come up with the magnitude? It's very simple, right? So the magnitude of the transfer function, once again, it doesn't matter as open loop transfer function or closed loop transfer function, okay, is equals to what? Now basically it just equals to, first of all here, the magnitude of the gain k here times the magnitude of the first fraction times the second fraction magnitude and times more if there are more, right? Denominator is similar. Magnitude of each term. Oh, by the way, I think this is not accurate, right? This is not gain. This is magnitude, right? Magnitude and the phase, not gain of phase. Okay, be very careful. This is the magnitude and the phase versus the frequency, not gain. Okay, not gain. Gain is part of the transfer function, not magnitude. These are two different concepts. Okay. So first, the magnitude here. Okay, the magnitude is equals to this, right? And how we come up with the function of the frequency, right? So based on these calculation of the magnitude, okay, we are saying magnitude of transfer function in Bode plot. Bode plot using 20 log 10 to the magnitude. Okay. First, you need to know the magnitude displayed in Bode plots is actually the 20 times log 10 of the magnitude of the transfer function. This is something you need to be very clear, because the magnitude you are reading is along the y-axis, right? This is frequency f. This is the gain. I'm sorry. This is the magnitude. Right. This is magnitude. However, this magnitude is the reading is equal to the 20 log 10 of the magnitude of the transfer function. Okay. This is the first thing you need to understand. Okay. This is the first bulletin. The second bulletin is actually, it equals to what? 20 log 10 magnitude of the transfer function of these magnitude is equals to what? Basically 20 log is equals to 20 log 10k. Sorry. Is basically equals to 20 log 10 of 8 times right. This is very straightforward. So we are looking for the 20 log 10 of the magnitude of transfer function is equals to what? Just equals this, right? This is very easy to understand. And this further equals to what? Anyone remember 20 log or any log function, let's say a times b divided by c times d equals to what? Mathematically, here equals to what? Anyone knows? How to expanding this algebra?
And subtract at the top and subtract the bottom.
Oh, very good, very good. 2 is right. Okay, 2 is absolutely right. It's equals to this, right? Summation for the numerator. Subtraction for the denominator. Does it make sense? In other words, the 20 log 10 a times b equals to 20 log 10 a plus 20 log 10 b. Right? And divide by c, and then divide by the d, it means minus 20 log 10 c, and then minus 20 log d. Right? Based on this algebra, and then we are expanding this, and then what do we got? The 20 log 10 a plus 20 log 10 of first guy and plot 20 log 10 of s plus z2 minus 20 log 10 s1 minus 20 log 10 sp2. Okay. Of course, here plus dots and then minus here dot. Depending on how many terms we have in numerator and denominator, right? Right. And here, S is a frequency dependent value, right? It's omega j. S is equals to omega j. And substitute into this result. What are we going to have? 20 log 10 k plus 20 log 10 and omega j plus z1 plus dots minus 20 log 10 omega j plus p1 minus dots. Right? Therefore, magnitude is frequency dependent value. Does it make sense? This is the magnitude, and magnitude only. Okay, how we come up with magnitude as a function of frequency? Here we go. S is frequency dependent variable. You have different frequency, then you have different S value. You have different S value, look at here. This is the magnitude, of course, under the 20 log 10. Okay, under the 20 log 10. This algebra is necessary. Okay, and this magnitude is actually the function of frequency, or say the magnitude is frequency dependent. Okay, so if you're sweeping different frequency value, you're gonna have different magnitude value. Okay. This is the magnitude. This is the magnitude. Okay. Similarly, if we study the phase of transfer function in Bode plot, phase. What do we have phase? What do we have for phase? We have phase of this, right? This is once again, if we do this, okay, this time is phase, and we don't have any other algebra, okay, like 20 log. No, we don't have 20 log now for phase. Phase is just a phase. Okay. Oh, Kevin is asking, do we lose somewhere as term in denominator? Yes. As term is here, and then we need to minus the 20 log 10 of as term here. That's right. Okay. We should have it. Log 10 as term. Okay, good. Okay. So, yep, when we try to find the magnitude, we should involve every term in both numerator and denominator. Kevin was right. Okay, Kevin was right. And then we going back to the phase. The phase here is obviously also we are looking for the phase for each term involved in the transfer function again, right? It's the first is k, right? The gain k. And then we have done this quite a bit back in the module 6. You're looking for each term's phase angle. This is exactly what we did in the module 6. The magnitude part is also similar to what we have done in module 6. The only difference I'm emphasizing here is red color, right? And emphasizing the difference, or say the new things to you by red color. Right? Red color means here, first of all, when we plot the Bode plot for magnitude, we need to use these 20 log 10. Okay. The other knowledge in blue are actually what we have learned. Yeah, the things we have learned. Okay. With that 20 log 10 thing, we have summation for numerator and subtraction for denominator. Okay. Out of here. And the phase of the transfer function here is the summation of the phase of the numerator minus the summation of the phase of the denominator, right? So we still remember the gain, the constant gain k here. What's the phase angle? Remember? 0. That's right. Very good. Okay, 0. So the gain of the transfer function is not affecting the phase of the transfer function, right? And then the phase to the rest of the terms is whatever it is, right? And whatever it is, we generally speaking calculate them by the calculator, right? By the calculator. And also here, once again, S is a frequency dependent term. So we will end up with 0 plus here omega j plus z1, omega j plus z2 plus dot minus omega j minus omega j plus p1 minus dot. And this is explaining why the phase of the transfer function is also a frequency dependent value. Okay, this is trying to explaining that. In other words, we have a conclusion down here. Phase is a frequency dependent value as well, right? In other words, the phase of a transfer function, whatever transfer function it is a function of frequency f. This is trying to explain that. Okay. Now, once again, don't forget this new thing, okay, in red color. Okay, the magnitude used in multiplot when you read the value is a log value. It's 20 log value. And if you need it, you want to go back to the real magnitude of the transfer function, you need to do what? Inverse log, right? Inverse log. There's an algebra involved. Okay, maybe you see the example for this. Okay. Any questions so far in terms of the concept of the magnitude and phase Bode plot? All right, and we can move on. It's probably very likely that it's not something new, but we just go through these basic concepts. Now let's talk about. I'm sorry. This is bulletin. Bulletin number 2. Okay, bulletin number 2. Let's talk about the open loop transfer function. Bode plot. Followed by closed loop transfer function Bode plot. Okay. These are two different transfer functions generated two different Bode plots, and we will respectively learn how much information, useful information, we are able to obtain from each one of them. Okay, let's begin with the open loop transfer function Bode plot. What this guy can do for us, okay, you got to remember, we are able to find something out of it. Okay, out of it, find what? So-called stability margins. Stability margins. Obviously, we need to first of all understand what does it mean by stability margins. Stability margins means first concept about it is how stable a stable system is. Okay. I don't know how much sense this make to you, but let me explain. What does it mean by how stable a stable system is? Stability margins is used on is trying to describe a stable system. First of all, the system must be stable. Okay, it's already stable. We know that. Okay, and then how much stable it is. We are studying this by the concept of stability margins. Okay, the system is already stable. If unstable, then your stability margin then makes no sense. Okay, it's already stable. However, how much stable? It still matter, right? That doesn't make sense. We all know that the system must be stable, otherwise it's meaningless for anything else. We are okay with this. However, stable system is still different from another stable system in terms of stability, right? The level of stability is different. Okay, it's different, and it matters. It matters, and it matters. Why it matters? And why it matters? Let's say with higher stability margin, the system gonna be what? Anyone has any thought? You have a higher stability margin, say one system. System A has higher stability margin than system B. Then what you are expecting from system A over system B? Any thoughts? Anything? Less transient. It's a blur description. A better transient. So if you have a higher stability margin, you have a better transient. Actually, not necessary. First of all, higher stability margins means what? Means this system is what? More stable. Does it make sense? How about this concept? Higher stability margin means this system is actually more stable. Then means what? Less overshoot. Less overshoot. I think that kind of concept is close. That kind of close. However, you need to specify it is open loop transfer function. Okay. Kevin is actually right. Okay, so you're gonna have less overshoot if you have higher stability margins for open loop transfer function Bode plot. Okay, closed loop transfer function Bode plot cannot give you that conclusion. But anyways, why has less overshoot? Why is that, Kevin?
Referencing back to those graphs when we talked about stable, marginally stable, and unstable. Because it's more stable, it follows the curve of what it's like the command curve. And the actual curve. The actual curve is going to follow closer to the command curve, so you're going to get less of the overshoot percentage.
Good, very good, very good, very good, very good. Listen carefully, everybody. The concept is like this: if the system is more stable, that means what? Means system has higher what? Damping ratio. Very good, very good. Sawyer is right. Sawyer got catch the point. It means you have a higher damping ratio, not better. Okay, then here we want to use higher or lower. Okay, you have more damping ratio. Damping ratio is trying to suppressing the overshoot. Does it make sense? Therefore, you have less overshoot if you have higher stability margins. Okay, so basically combining Sawyer and Kevin's answer, we are reaching the correct description. Okay, we can say in this way. Okay, we can say in this way. Higher damping ratio. And this lower overshoot. Okay, very good point. Very good point. And this means what to a general system? It means the system is able to withstand greater change in, say, system parameters or environment before becoming unstable. Does it make some sense? You have high stability margin. That means your system is able to withstand greater change in system, like system parameters or environment, operation environment, before becoming unstable. Because if you have a very dramatic change in system parameters or operation environment, it's very likely making your system become unstable, right? Very likely. However, if you have big enough stability margin in your system design, then you're able to withstand more change like those. Okay, this is the concept of the stability margin. Okay, it matters. In other words, once again, how stable it is matters. Okay, how stable it is, it matters. Okay, you know, both systems are stable, good. And how stable they are relatively, it still matter. They still matter. Okay, this is the stability margin concept. Okay, and then the next thing you need to know is we have two stability margins. One is the gain margin. GM. Second is the phase margin. PM. Okay. And we have, why we have two stability margins? Okay, because one is from magnitude body. The other is from the phase body. Right? Remember, we have two. One is magnitude and other phase. From magnitude body, we can find the gain margin, GM. From the phase magnitude phase body plot, we can find a PM. Okay, just simple as that. And then let's brief the description of them respectively. So the GM means the change in open loop transfer function gain required to make the closed loop system unstable. This is actually making sense, very meaningful. So we are talking about it, first of all, in open loop transfer function, the gain. If you change it, how much change you can do before making the system become unstable, right? And when we talk about the system stability, we are talking about the closed loop system stability, okay? This is a very, very important concept. Is your system stable or not? Which system we are talking about? Definitely not open loop. Open loop system, it means nothing to us. All we care is closed loop system stable or not. Okay. We use different color to emphasize this one more time here. Stability means to closed loop system, okay, not open loop system. We are using open loop transfer function body plot to find the stability margins for closed loop system, right? Remember this rule, okay? Don't mess this up. Don't mess this up. It's just like in the previous module, we use what? We use the open loop transfer function to find the root locus, who is the path of closed loop poles. Remember? Here is a similar pattern. We are using the open loop transfer function body plot to find the stability margins for a closed loop system, because we don't care the open loop system performance. We only care about the closed loop system performance. However, we are using open loop transfer function. Everyone is following, because this is a very important concept. Okay, not surprised that we will have a multiple choice again, and obviously these are all good subjects, good materials to be used for those assessment, right? Right, so this is the GM, and the PM is similar, right? So it means the change in open loop transfer function phase required to make the, once again, closed loop system unstable. Okay, once again. These are the concepts of the GM and PM. Next, let's talk about how to find them. Okay, how to find.
When you say change, the change, what are you referring to? Could you maybe explain more what you mean by the change is the open loop transfer function gain? Like the value that we're finding?
Well, first of all, the given system transfer function is fixed, right? And so you can plot this. You can plot this body plots, right? And the frequency in this one particular system, you have one particular frequency, right? And that particular frequency points you have respectively magnitude value and the phase value, right? From that point on, as a reference, you start to change your system gain to make your system unstable, and then that change is the gain margin or phase margin. Does it make some sense?
Okay, so just to make sure that I got that, it's the open loop transfer function that we're plotting the Bode plot of, right? And then that, let's say at that particular frequency, that magnitude that we basically calculate for, that is the change that it's referring to that we'll see on the output of the open loop transfer function?
Not output of the open loop transfer function. Given a system, you plot the Bode plot right away, right? By MATLAB, okay? By MATLAB, we don't have to use the hand calculation. But MATLAB, we plot the Bode plots, right? And then if you change the gain, what's going to happen is the magnitude Bode plots going to shift. Does it make some sense? Actually, shift up or down, right? I shift up or down. It's going to change. So
so that gain margin, if it, say, for example, was 10, let's say we found at a particular frequency, let's say that the closed loop transfer function gain margin at that frequency was 100. Would that mean that it could be 110? Is that what you're kind of implying, or?
No. Gain margin can only be obtained by open loop Bode, okay? You can't use the closed loop Bode to find a gain margin. If this is too hard to imagine, let's go on to see a specific example.
Okay.
Maybe it makes more sense. At the beginning here, without visualizing it, probably it's not easy to see what does it mean. Okay, let's go over example, but later. Okay, let's talk about first of all how to find the gain margin and phase margin. Okay, this is obviously very important. Okay, very important. So first, how to find a gain margin. Of course, before anything else, remember in open loop transfer function body. Okay, very, very important. You are not going to find GM and PM from the closed loop transfer function body. Okay, you can't do that. Okay, and remember the title of this part is open loop transfer function body. What we can do is find GM and PM, not closed loop transfer function body. Okay, be very clear at the first place. Okay. Now let's talk about how to find them. Okay. The body, like I said, generated by MATLAB. Okay, let's see how to find them. The GM is the difference between 0 dB and the magnitude at, of course, this magnitude also in dB. It's also in dB. What does it mean by dB? dB here is the unit of 20 log 10 of your magnitude, right? dB is the unit of 20 log 10. Remember, in the body, you're using 20 log 10, right? You're not directly using the magnitude. You're using 20 log 10 of that magnitude. The dB is just the unit for it. Okay. So GM is the difference between 0 dB and the magnitude at the frequency. Which gives 180-degree phase. And when we do calculation, it's just GM equals to 0 dB minus that dB value you get from here. PM is the difference between negative 180-degree and the phase at the frequency which gives 0 dB in magnitude. And we are following this equation here too. Minus negative 180-degree. And of course, also equals to this guy plus 180-degree. Here, let's read them through. Okay, yeah, it's a little bit confusing, but actually, it's actually absolutely logical. Okay, let's see. So the GM, how to find it? We need to read open loop transfer function body. We need to read. Okay, how to read? GM is difference between the 0 dB and a difference between the 0 dB and the magnitude. What magnitude? That magnitude is at the frequency, which gives you negative 180 degree in phase. So what you want is find the frequency first. Okay, the frequency which gives you 180 degree in phase. The frequency who can give you negative 180 degree in phase is called phase crossover frequency, omega PC. Okay, the frequency who can give you negative 180 degree in phase is called phase crossover frequency, omega PC. And in PM, we are looking for the difference between the negative 180 degree and the phase at the frequency who can give you 0 dB in magnitude. Okay, so the frequency which can give you 0 dB in magnitude is called gain crossover frequency. Okay, omega GC. The subscript here is GC. So G represents the gain. This is the GM and PM concept, and by using which, let's do a very small example here. Okay, I list these page here, and let's try a very small example. I call it example 0. So imagine we have open loop transfer function body given plots given below. Let's find omega PC, omega GC, GM, and the PM. 4 things. Okay. And who are these 4 things? Going back to this concepts here, GM, PM, 2 values based upon the red color equation here to calculate, right? These are GM and PM. And the omega PC and the omega GC are 2 frequency in black. Okay, these are the 4 things we are going to find. Okay. Let's see how to use these, how to apply this concept. Okay. First, we need to assume body plots like this. Okay, body plots like this. First, the top one is the magnitude body plot. The bottom one is the phase. In degree. Okay. So the magnitude is like this. Let's assume it looks like this. The magnitude body plots like this. Okay. And let's assume the phase Bodhi plot look like this. Okay. I'm not labeling anything. However, let's go through this concept, this concept procedure. Try to see how we can find two frequencies and two margins. Okay. So first of all, let's read the two frequencies first. Okay. So first of all, the phase crossover frequency, omega PC, means what? The frequency gives you negative 180 degree in phase. I think this is straightforward enough, right? So what do we need to do? Go to the phase Bodhi plot first and locate negative 180 degree, right? Locate negative 180 degree. For example, negative 180 degree is down here, right? And what we need to do is just find the intersection with the Bodhi plot, which is this point. And then we go up to read the frequency. So this frequency is omega PC. Does it make sense? Because according to the definition here, the frequency gives you negative 180 degree in phase is omega PC, phase crossover frequency. Here, we locate negative 180 degree for phase and then find what's the frequency here, right? This is the omega PC, done. Second, we are looking for the omega GC, right? Omega GC means what? The gain crossover frequency. So it's the frequency giving you 0 dB in magnitude. Okay, we go to the magnitude Bodhi plot here. So where is 0 dB? Now, for example, if you're assuming here is 0, okay, I know my axis is plotted here, but that not necessarily is definitely the 0 dB, right? So my 0 assume to be here, and then what do you want to do is 0 dB go to intersection with the magnitude Bodhi plot, and then you go down to locate this frequency along the x-axis, omega GC. Does it make sense? And here, both magnitude and phase are sharing the same axis, the same frequency axis. Okay. So here is omega GC, so is here. Here is omega PC, so is here. Right? That's not a problem. Right? So any questions regarding the omega GC and omega PC, how we find it? Just not according to the definition, right? Omega PC is in phase. The frequency gave you negative 180 degree. Omega GC is in magnitude, where gave you 0 dB. Right? This is the definition for omega GC and the PC. What you need to be careful is the unit here. Is you're reading here, okay, this is in frequency, in hertz. Then your result here is in hertz as well, right? All right, we can move on here. Okay. So next, let's find the GM and PM. How to find GM and PM? Okay, I'm using the black. Let me use the red. Okay. So going back to the definition here once again, so GM equals to 0 dB minus question dB. Okay, question dB means what? Is the dB value at omega PC. Okay, be very careful. This question is equals to the magnitude in dB at omega PC. What do you need to do? Go back to here. We already labeled omega PC. Omega PC is here, right? This is omega PC. And then what is the magnitude at here? It's here, right? You read it. Does it make sense? At this point, and then you read it here. For example, let's say this 95. And you know the unit as dB, okay? Be very careful. The unit here is dB. So 95 here means negative dB. This gives you what? GM equals to 0 dB minus, what is it? Once again, negative 5 dB equals to what? 5 dB as the GM. Does it make sense? Because here is telling you that your question dB here is at what? Omega PC. Right? Similarly, how to find the PM? The PM is equal to question degree minus, or actually plus 180 degree, right? How to find this question? That question degree is at the omega GC. Reading omega GC, omega GC is already labeled here. And then find the phase, right? To find the phase, you go down to here. Intersection with here. And then you read degree along the y-axis. For example, this degree is negative 150 degree. And then PM equals what? Negative 150 degree plus 180 degree, right? Equals to positive 30 degree. Does it make sense? Nothing but following the given definition here. Okay. Any questions? All right, if this is fine, then we move on. Once again, this is using the open loop transfer function body to find the PMGM and omega PC and omega GC. Okay. And this next, let's talk about what can we do with the closed loop transfer function body plot. Okay. What can we do about from here? Okay. What this guy can give us. This guy can also help us to find something else, obviously, something else, right? What can we do? We can find a BW. What is BW? This should be a very familiar term, right? Yes. What is it too?
The bandwidth.
Very good, bandwidth. Okay, just the bandwidth. Yeah, we use this a very familiar term. Okay, bandwidth. Similarly, we are not going to be able to find the bandwidth from the open loop transfer function body plot. Okay. Once again, I have emphasized this more than 5 times today. Okay. 2 different transfer functions give you different body plots. Okay. They are giving respectively different information as well. You can't mess up. You're looking for the bandwidth from the open loop transfer function body plots. No, the result no way to be right. Okay. No way to be right. Okay. We're looking for bandwidth from the closed loop transfer function body. Okay. And what else? Okay, there's one more thing we can find. Okay, that's a very interesting is find a particular output signal. upon a given particular input. Okay. In other words, if given a specified input signal, we are able to find the corresponding particular output signal. Here, since we are talking about a frequency, so obviously we are talking about the sinusoidal input and sinusoidal output with different frequency. I mean, with same frequency, but with different magnitude and phase, right? VVC. Right? Find two things out of closed loop body. So first, the bandwidth is the bandwidth is a frequency. Okay, first of all, the bandwidth is a frequency. Bandwidth is not magnitude, not phase angle, but a frequency. Okay, you need to understand this. Okay, your bandwidth equals to like a 50 hertz. That at least makes sense. If you end up with 50 dB or 50 degree, definitely wrong. It's a frequency at which the magnitude is 3 dB down from 0 dB. And the second thing, we can find a particular output. How to do this? This is actually based on a simple fact, right? Output over input equals what? Gain. We call it gain in 318 or 358, but in 360, what do we call it? Transfer function, right? But be very careful which transfer function. You need to understand this. Which one? Closed loop transfer function. Okay, you can't use open loop or any other types of transfer function. It has to be closed loop. This is actually the definition for a system transfer function. When we talk about a system transfer function, we mean nothing but closed loop. Okay, closed loop. And based on this, we can find what? We can find your magnitude of the output and the phase angle of the output, respectively. Right? So your magnitude of the output equals to what? Magnitude of input times magnitude of closed loop transfer function. Phase of the output equals to what? Phase of the input somehow with the phase of the closed loop transfer function. Anyone knows what is the operation in between here? plus. Very good. Very good. Why is that? Why is that? It's just like this, right? You say output, let's see, output equals to what? The input input magnitude, input angle times the transfer function magnitude and transfer function phase angle, right? Because of here, you see, output equals to input times closed loop transfer function. Okay, then your output it just equals to the product between two phasors. Then your magnitude of the output equals to what? Magnitude I times magnitude G, right? Phase angle of output equals to what? Does it make sense? This is what. Okay, this is what. You have this. Of course, to once again, you need to specify or say you have to be given a particular input. Okay, without input, you can never find output signal. Okay, you have to specify the input. Any questions before we go into real example 1, actually, as well as 2? Any questions regarding these concepts? All right, if these are fine, then let's take a look at the real example. Okay, real example. Let's see how to solve them. Here is the real example 1. By the way, the example 1 and 2 have been posted in the Canvas module 8, so you should be able to access them. Today, probably we are able to finish half of the example 1, and then let's see. Okay, so here, example 1, the system body plots, including both open and closed. 2 body plots. Okay. By 2, I mean open loop and closed loop. Okay, and in each one, excuse me, in each one of them you have magnitude and phase, right? And they're respectively displayed in figure 1 and 2. So this is figure 1. In figure 1, once again, you have magnitude and phase, okay? Top and bottom, 2. Right? This is the open loop body. We label and find the system gain crossover frequency and the phase crossover frequency, right? Omega GC and omega PC. Right? And here, the frequency here, like the concern from John, the frequency here, be careful. Be very careful. It's not hertz, but radian per second. Okay. So when you reach the omega PC and omega GC, you are using radian per second as well. But if the generated bodies are in hertz, you're using hertz. So you need to read the given units. You need to be carefully reading the given units. Does it make sense? So here, the omega GC, once again, if you check your notes, omega GC means where the frequency at where you're reaching the 0 dB, right? So omega GC. Therefore, where is it? 0 dB. 0 dB is here, right? Can you see it? 0 dB is here, right? Reading the 0 dB magnitude, then 0 is over here. And you intersecting with the curve by about this point, right? About this point. I'm using the center of my cursor to locate the intersection point. Therefore, what is the frequency value here? Anyone can read to me? What is the frequency value? Anyone can read this frequency value? Around here. Anyone? Well, Sawyer's answer is 0.1. 0.1 is not considered as wrong. However, if we locate this very point here, then what is it? 0.1 is here, right? Because 0.1 is going down to here. Right? This point is 0.1. However, here is what? The pointer is in the way, okay, like this. How about now? 0.1 is okay. John's answer is 0.09. It's better answer. 0.09. Okay. This line here is 0.09. Very good. Very, very good. Okay. Once again, this line here now is labeled as 0.1, 10 to the negative 1. The left line right next to it is 0.09. Does it make sense? It's 0.09. Okay. By the way, have you guys learned how to rate the logarithmic axis like this? Because this x-axis is a frequency axis, and it is labeled in logarithmic. It's not linear 1, 2, 3, 4. It's like that. No, it's not like that. It's labeled in log. That's why you're seeing the vertical grid is not linearly aligned, right? Because it's in log. Have you got log is like this? Okay, log is labeled in like this. Okay, nice. This is the x-axis, right? Okay, line. It's labeled in this way. Now, for example, what we have here is the first one is 0.1, maybe 0.01. Okay, the first labeling here could be any value. However, the next one is 10 times of this value. Next division here is meaning 10 times of it. 10 to the 0. Does it make sense? Next here is what? 10 to the 1. Next here is 10 to the 2. Every 10 times is linearly assigned, or say aligned. This length is same as this length, same as this length. Okay. 10 times is linearly, every 10 times is linearly distributed along the x-axis. So generally speaking, when you read it, you will be able to see these labels here. Okay, and you can notice that actually these every 10 times is linearly distributed. Okay. However, within each division, it is nonlinear. It's nonlinear. Specifically, it's like this. So 0.1 to 1, right? This is 0.1 to 1, obviously. So where's 0.2? 0.2 is actually almost 1/3 of it. Okay, this point is almost, this is 0.2. 0.3 is less. 0.3, 0.5, 0.6, 0.7, 8, 9, so on and so forth. So the distribution of these divisions within 10 times is actually nonlinear. So when you read it, you know this is 0.1, okay? This is 1, okay. The next division from 0.1 is 0.2. Following at 0.3, 0.4, 5, 6, 7, 8, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this 8. And the very last was 0.9. And then 1. Does it make sense? The same thing, we use the second division as example. So here's 1, here's 10. Okay. Then the first reading here is what? What is it? Anyone? 2. Here we go. Next one. 3, 4, 5, 6, 7, 8, 9. And then 10 right here, right? And then the following, this is a 10, this is 100, obviously. This is 10, this is 100. So the first division here is what? What is it? Anyone knows?
20.
20. That's right. And then following that's the 30, 40, 50, 60, 70, 80, 90, and 100. So the tricky thing is that they're not linear. Okay, they're not linear. You have to first of all locate these points, right? These 4 points for 0.1, 1, 10, and 100. Well, according to the given labeling, okay, because it might be from 1, 10, 100, 1000. That's possible. Or 0.01, 0.1, 1, 10. That's possible too. Okay. And by reading the given axis, you should be able to read those, the major divisions. Okay, the major divisions. And then between each one of them, between any two of them, or say, between any two of them, that one division, you need to be careful as from where to where it's representing how much. Because obviously this one division here is representing what? 0.1, right? However, this division, one division is representing what? 1. This is representing what? 10. They are different. They're different. Does it make some sense? You guys never do anything like this before? Or oh yeah, because if you're generating the body plots from the software, guess what? You move your cursor and then read the value, right? That's very simple. So you don't have to read the value from reading the graph, because if you move your cursor over the point, the value, frequency value, the magnitude value, the phase value gonna automatically display it, right? That's why you don't need to worry about it. That's why you don't need to worry about it. So 335, ever taught it? Oh, Sawyer asking a good question. Is this logarithmic falling log 10 or 20 log 10? This is log 10. Okay, there's no 20 there. 20 log 10 is talking about the magnitude of the Bode plot. Y-axis. Now we are discussing the x-axis.
If the x-axis happened to be what Sawyer was mentioning, 20 log 10, would the labeled units then on the axis be frequency dB radians per second or no?
No. I'm telling you, x-axis won't be used as 20 log 10. It won't be, just a log 10.
Okay.
As 20 log 10 only applied onto your magnitude, which is y-axis. You can't do 20 log 10 along the x-axis. Any other questions? All right, thank you for attending today's lecture, and we're gonna finish these two examples by next lecture. However, I strongly suggest to all of you guys try the mod by yourself, based on what you learned from example 0. Okay, really try these two examples out by yourself, and then by next lecture we're gonna quickly go through the solution. Okay, very important, and it won't be surprised that this going to be one of the exam problem. Okay, do this yourself. Okay, do this yourself before next lecture. Okay, and this is very, very helpful. All right, now that's all for today, and talk to you guys on Wednesday. Bye now.